The last example today, it looks more complicated, but actually it's not. Okay, the figure is shown here. Loading is added to both ends. It's overhanging on both ends. Okay, it's W1 and W2 are added to it. So you're requested to calculate, to determine the deflection of the beam at the point A. Right, at point A here, this free end of a cantilever part. Right, this, first of all, let me ask you, just look at this. How many beams are you planning to split it into? 3 or 4 or more? Right, so directly it's logical to just split it at these two connections at point B and point C, right? So after splitting, you will get 3 or 4 beams. You can name them. Right, so the first part between A and B will be the beam 1 here. It's a cantilever subjected to a distributed load. Right. Then the BC will be a beam 2, simply supported beam subjected to a bending moment from W1. Right. So let's name it MB, and this MB can be calculated, which is equivalent to this concentrated load, the distributed load that's concentrated to here. So this MB can be calculated as 45 by it equals the W1 by the AB. The AB is A, right? It's here, the A. So W1 by A times A over 2. So this is how you calculate the MB, right? So this in the beam 2, the simply supported beam will be subjected to a concentrated MB that can be calculated using this equation. Okay, then the right hand side, you have another cantilever that is our beam 3, but this beam 3 will not lead to any deflection components at point A. Since it's a cantilever beam, everything will stop at this fixed end. Okay, so all of its effect will be reflected by a resultant bending moment MC. Right, in this MC can be calculated from W2 times C over 2. Right, this is the equation you calculate the MC. But when the MC is added to the simply supported beam, it will curl this beam BC upward, then leading to another deflection component at the free end A. Okay, so as I summarize this, you will just need to do 3 calculations rather than 4, right? Since the delta A at the free end A will have 3 components. This is the delta 1 here, and delta 2 prime here, and delta 4 prime here. So you just need to do calculations for these 3 components. And let's look at the first one, the beam 1. We have been very familiar with this. Without looking and know it's equation 29. And let's double check. Okay, here, right? This is a cantilever beam subjected to distributed load. So we'll use equation 29 to calculate the downward deflection. So this is equation 29. Right, so the delta 1 can be calculated as is negative WL4 to the 4th over 8 EI. And this will be 45. This is W1, okay? This is 45 by the L here. L here's AB. Okay, here this is a typo here. It's 1.2. Okay, the 45 by 1.2 to the fourth over 8 times the EI is 7,500. Okay, here is 0.00156 meter, and this is a downward component. Right? Of course, you can add this negative sign since you have a negative sign here. So you can add a negative sign here. But as we mentioned in the previous example, this is not very important, since if you understand this is downward or upward deflection, the negative positive sign will be less important. Okay, then let's look at beam 2. So the beam 2 is a simply supported beam, right? Simply supported beam subjected to the MB. Right, so first of all, our MB need to be calculated, and that is, as we mentioned, it's W1 by A over 2. It's 45 by 1.2 by 0.6. Then you will get 32.4 kilonewton meter. Again, strictly speaking, this is a negative bending moment, right? But we can ignore the sign, as I mentioned. Okay, we ignore the sign. We only analyze will it lead to positive upward or downward deflections. Okay, then we can calculate the theta 2. Right, this theta 2 here. Again, which equation we use? I remember there should be equation 7 here, the equation 7. Right, so this time is the near end. We're calculating the slope at the near end, just nearby the bending moment. So we'll use the theta 1. Okay, we'll use the first equation, theta 1. So theta 2 equals, here, just we use the theta 1 equation. Okay, just MB L over 3 times EI. This is 32.4 by the L here is BC. The B is 4.8, right? 4.8 over 3 times 7,500. You get 0.00691 radian. Okay, let's denote it. This will here we're using equation 7, the first equation, to calculate the theta 1, or in our case it's theta 2. Then the component delta 2 prime can be calculated from this triangle here, right? In this triangle here, this is the angle equals delta 2. And we have B here, you have A here. Right, so the delta 2 prime can be calculated from AB times delta 2. And AB is just A, is 1.2 meter. Right? This you get a 1.2 meter times 0.00691. And you get a 0.0083 meter. And again, this is a downward deflection as shown here. Then we have beam 3. On the beam 3, as we said, beam 3 will not make any changes, will not lead to directly any deflection at point A. So all of these effect is reflected by the bending moment MC, right? So we will not calculate beam 3, we directly go to beam 4. Okay, the beam 4 here, we're calculating a theta 4. And this is this angle here, the theta 4. And again, we'll just use, I believe I will use equation 7 again. Equation 7 here, but since this time your bending moment is at the far end, so we'll use the second equation. Okay. So here the equation we'll use will be equation 7, but it's the far end equation, so theta 2. In our case, this time is the theta 4. Okay. The theta 4, of course, at the beginning we need to calculate the MC. Okay. MC equals W2 by C over 2. That is 20 times C, or C value is also 1.2, right? It's 1.2. Let's give it here. We didn't give this number. C equals 1.2 meter equals A. Okay, this times 0.6, and you get you got 14.4 kilonewton meter. Then the theta 4, as we said, we'll use the equation 7's second equation. So the theta 4 can be calculated as MC times L over 6 EI. Right here is ML over 6 EI. Okay, this will be 14.4 times the L here. Again, it's a 4.8 meter over 6 times 7,500. Then you get 0.00154 radian. Again, now we can examine this triangle. And you have this angle here, theta 4. You have B and A. Right, so the third components of the deflection at point A, delta 4 prime, can be calculated at AB times theta 4. Okay, that is 1.2 meter times 0.00154. You will have 0.00185. Again, this is another downward deflection as shown here. This is a downward deflection. So, in the end, the overall deflection at point A can be calculated by summing all of these three components, right? So we have the component 1, component 2, this is component 2 and component 3. All of them are downward deflections. You just add them together, okay? We have 0.00156 plus 0.0083 plus 0.00185. Then you have 0.0117 meter. But it's important to note that this is a downward deflection, or actually a negative deflection, since all of them are downward components.